let us see this popular recursion problem. In this problem, we have three towers, A, B and C. There are certain disks which are placed in tower A, and our target is to move these disks from tower A to tower C. We need to use tower B as an auxiliary tower. So for example, in this particular question, when we have one disk, we need to move this disk to here. In this example, we have two disks, we need to move these two disks here. In this example, we need to move these three disks from here to here. And when we are moving these disks, we need to move them in the same order. The largest one should be at the bottom and the smallest one should be at the top. Now, while you are moving these disks from tower A to tower C, you need to follow certain rules. The first rule is only one disk can move at a time. The second rule is we need to have this order always, that largest is at the bottom and the smallest is at the top, even in the intermediate steps. The third rule is we can move only the top disk. We cannot take out a middle disk and move it to C. We can only take the top disk out and move it to any of the towers. Let us understand the problem better with these examples. We are given a number n, which is number of disks placed in tower A. And we need to print moves to be done to place these disks from tower A to tower C following the given rules. So in this particular example, we have only one disk. We can directly move it from A to C. Right? So our output move is move it from A to C. In this example, we have two disks. So these are the moves. We first move the disk 1 from A to B. So we take this out and move it to B. This is our first move that we follow. So we are following all the rules. We are only taking out the top disk. We are not picking up the bottom disk and moving it here. We are first taking out the top disk. And this disk 1 goes to tower B. Now the second move is move disk 2 from A to C. So we move this from this A to C. This is disk 2. Now what are we doing? We are saying move disk 1 from B to C. So we move this from this to C. And you can notice that we have both the disks in the same order in tower C, and we followed all the rules in every step. Now please pause this video and think of a solution that you will do to move these three disks from tower A to tower C following these rules. Here is solution for n equal to 3 disks, and this solution requires 7 steps. These 7 steps are shown here. First we move the smallest disk from A to C, then we move the second disk from A to B, then we get this. After getting this, we move this disk 1 back to B, so we get this. Now we move the third disk to tower C. So third disk reaches its correct position. And after that, we move this disk 1 to here, right? And after that, our task is to simply move 2 here and then 1 here. That's what we have done in these 2 steps. So we need here these total 7 steps to solve this problem. Now, can you think of the solution in terms of recursion? If you have a problem for n equal to 3 disks, can you use the solution for n equal to 2 disks and solve this problem? Please pause this video and think of a solution that uses a solution for n minus 1 disks. You may try for n equal to 4 disks and then see how can you use the solution for n equal to 3 disks. And if you take a look at this solution, we can use the solution of n equal to 2 disks to solve the problem. If we take a closer look at the solution for n equal to 3, we can notice that the first thing that we are doing is we are moving these 2 disks from here to here using this C tower as an auxiliary tower. So initially our source is A, our destination is B, and C is auxiliary, and we recursively move these n minus 1 disks from here to here. And that's what we get after the first recursive call for n minus 1. Once these 2 disks are moved from here to here, we move the nth disk or bottom disk from here to here. We move it from A to C. That's a simple step. Move one disk from here to here. Now, we again recursively move these n-1 disks from here to here using this as an auxiliary. And that's all is recursive solution. First, you move n-1 disks, top n-1 disks from A to B using C as an auxiliary. Although C is your final target, but in this recursive call, you use C as an auxiliary tower. Then you move the bottom disk from A to C, which is a simple disk movement. You can notice this recursive function that I've written here. We first move the n-1 disk from A to B using C as an auxiliary. And then we move the bottom disk or nth disk from A to C. Right? That's what we have done here. So first recursive call will take care of all these steps. Right? It will simply recursively call for n equal to 2, which will take care of all these steps. Now you will move the disk n, which is the bottom disk, from here to here. Now your target is to move these two disks from here to here, and you have an auxiliary tower to solve this problem, right? So this time you call again for n-1, you use B as source, C as destination, and A as auxiliary. And after this recursive call, these steps will happen and you will get your final output. So that's how we can solve this Tower of Hanoi problem recursively using the solution of n-1 problem. Now please pause this video and try to write down complete solution in your favorite programming language that prints all moves for n disks. Here is recursive implementation of this approach in C++ and Java. So what we do here is we first move n-1 disks from A to B using C as an auxiliary. Then we move the bottommost disk from A to C. Then we move n-1 disks from B to C using A as an auxiliary. And the base case is, if you have only one disk left, then you need to simply move it from A to C, right? And you need to print this move. So you have two print statements when you have on n equal to 1 only, and when you have middle statement, which is for the bottom disk. Let's now see the working of this recursive code for this example with two disks. So when you call this for two disks, what will happen? You will recursively call for one disk, and when you call it for one disk, you will be using B as a destination and C as an intermediate. Now when you call for one disk, what will happen? It will simply go into the base case and it will move disk number 1 from A to B. Right? That is what it will print. Now your control will come back to the main recursive call, which is for 2, because this recursive call went into the base case and finished. So when control comes back to this recursive call was waiting for this to finish. So it has finished. It will begin with the next line and it will execute this next line. When it executes the next line, it's going to print move 2 from A to C, right? Move disk n from A to C. That's what it's going to print. And after that, it's going to make a recursive call for n-1 disks with B as the first tower and C as the target tower. So we are going to call for BAC. B is your source, C is your target, A is your auxiliary. So when you make a call for this, you will call with these parameters BAC and it will print move disk 1 from B to C. Because when you're making a recursive call, your variable A now holds, which is a char variable, it now holds the value B, right? And variable B holds the value A. So they will print this. And this is your final output. You can notice that these steps are valid. First thing that we do is we move disk 1 from A to B. Then we move disk 2 from A to C. And then we move disk 1 from B to C, right? B to C. And we get this. Let us see the working of this recursive code for 3 disks. So we initially have tower numbers as A, B, C. Please note that these values written in single quote are values for towers and these are variables. So initially A is A, B is B and C is C. But during the recursive calls, it might happen that this variable A gets a value which is not A, right? In this recursive call, for example, A gets C, and in this recursive call, A gets B, right? So these are just variables and these are actual values assigned to them, tower numbers actually assigned to them. Now in this recursive call, when you call for 3 ABC, it begins its execution from the first line. It checks n is not 1. So it comes out of this base case, does not go into the base case, comes here. and then recursively calls for n minus 1. So it calls for 2. And when it calls for 2, it changes B and C. So now our C becomes B and B becomes C. And when you call this function, this again begins execution from the first line. And in this recursive call again, n is not 1. So it's going to call for 1, right, n minus 1, and it's going to again change B and C. So B becomes B again and C becomes C. Now, when you make this recursive call, it begins its execution from the first line. It checks n as 1, right? So it goes into the base case. And when it goes into the base case, it simply prints move 1 from A to C. So this is our disk number 1. This is moved from A to C. This is what happens in this particular part of the code. Now this one function finishes and gives the control back to the function for 2. When it gets the control back, it was waiting for this particular line to execute or this line to execute in C++. So it executes this line and it prints move 2 from A to B. So what happens now? This disk is moved from A to C, right? This movement happens. Now you again call one more function, which is the third line, right? Third line in the recursive calls, and it calls for n minus 1 again for 1. And this time you change A and B, which means A is your A and B is your C, right? So we change these two and we call for CA. So when you make this recursive call, it falls into the base case and it moves one disk from here to here. So one disk is moved from C to B, right? Disk number 1. And this recursive call is over. So it gets the control back to the main caller, and this caller has finished all the statements inside it. Now this call is finished. So it gives the control back to this caller, and this now executes its next line. And its next line is this line, right? Or this line. So what it does, it moves the disk n, which is disk 3 from A to C, right? So you get this line on the screen. And disk 3 is moved from A to C. So this comes to the tower C now. Now once this is done, it's going to make the second recursive call here in this line. It's going to make this recursive call for n minus 1, which is for 2. And this time B and A are going to be changed. So it makes a recursive call for 2BAC. And this recursive call works similar to this recursive call and prints the required movements, right? So we get these movements one by one. So this is how this Tower of Hanoi recursive calls work for n equal to 3. So we understand the recursive function now. Let's quickly take a look at the disk numbers. How does this recursive function ensure that we get the correct disk numbers printed on the screen? In this recursive function, we print 1 here and we print n here. So how are we getting the correct disk numbers from this recursive call? Let's first understand it for n equal to 2. If we understand it for n equal to 2, we can quickly relate the higher values. For n equal to 2, what happens is we number the disk as this. The top disk is numbered as 1, the bottom disk is numbered as 2. Now in the first recursive call, we move the top disk. We recursively call for n minus 1, which means we move the top disk from A to B. We use C as an auxiliary, although it's not used, but in our recursive call, C is passed as an auxiliary, A is a source and B is destination. So it works fine for this part. Then after we have made this recursive call, we move the disk number n from A to C, which is disk number 2, which is the bottom disk. So we move it from A to C. This is also printed correctly. And once we have done this, we move the top disk, the disk number 1, from B to C. So we also get this part correct because you're making a recursive call with B as source and C as destination, and this recursive call is called for 1. It's simply going to move the one disk from source to destination, right? So we get all the outputs correctly for n equal to 2. So we get the correct result for n equal to 2. Now how does this work correctly for n equal to 3? When n is 3, what will happen? You will make first recursive call for the top 2 disks. You will make a recursive call for 1 and 2. And in this recursive call, you will move these disks from A to B using C as a intermediate. So when you make this recursive call for top 2, and we have seen that this recursive call works perfectly fine, it gives you the correct disk numbers. So these 2 disk numbers will be moved correctly from A to B, right? They'll be moved from A to B correctly, and you will get the correct disk numbers that we have seen when we called for n equal to 2. So these 2 will be moved and your correct movements will be printed by the recursive calls. Now after this, what are we going to do? We are going to move this disk from A to C. And what are we going to print? We are going to print move disk N from A to C, which means move disk 3 from A to C. And this is fine, this is correct statement. So we'll get this disk, bottom disk from A to C, and we'll get the correct output statement. Now once we have moved disk N from A to C, we are going to make a recursive call for N-1 again with C as B as source and C as destination. And this is again a recursive call for 2 disks. And we have seen that it works great for 2 disks. So we are going to get the correct disk numbers for this recursive call also. And our A, B, C are going to be modified like this. We are going to get the correct disk numbers on C. And since the recursive calls for 2 work fine, we are going to get the correct disk numbers in this movement also. So we got all disk numbers correct for n equal to 3. Using the similar argument, we can prove for n equal to 4 also. Because for n equal to 4, what you will do? You will move the top 3 disks from A to B first. And it works for a top 3 disks. It gives you the correct disk numbers, so we will get the correct disk numbers. Then you will print move disk 4 from A to C, which is fine, which is correct. And then you will again move the top 3 disks from B to C, which also works and prints the correct disk numbers all the time. We have seen for n equal to 3. So this is how we can argue that it gives the correct disk numbers for every input. Let us now try counting number of movements for a given number of disks. When we are given 1 disk, we need only 1 movement. We just need to move it from A to C. When we are given 2 disks, we saw that we needed 3 movements. When we were given 3 disks, we needed 7 movements. Let's now try to come up with a formula for counting the number of movements for an n. When n is 1, we need 1 movement. For a given random n, we call it for n-1 2 times, right? Those many movements required, then we make a movement also. So we call for Tn-1, we make a movement, and then we call for Tn-1. So 2Tn-1 plus 1. These many movements we do for a given n. Let's now try counting this value using the recursion tree method that we have discussed. So in the recursion tree method, what we do is we write the non-recursive part here as the root, and then we write recursive parts as children. Now again, we extend these recursive parts. We write the non-recursive part here, non-recursive part here, and recursive parts of these. So Tn-1 can be extended as 1 plus 2Tn-2, 1 plus 2Tn-2. And we see a pattern now. So in the recursion tree method, we stop whenever we see a pattern. And pattern is these numbers are doubling. We have 1 here, then 2 here, then 4 here. So we can notice that the series that we are going is to be something like this. 1 plus 2 plus 4 and so on. And what will be the last term of the series? If you see for n equal to 3, you will have 3 terms. For n equal to 2, you will have 2 terms because you will stop at n equal to 1, right? You have a base case for n equal to 1. So our last term is going to be 2 raised to the power n minus 1. We are going to have n terms with the first term as 2 raised to the power 0 and last term as 2 raised to the power n minus 1. Now if we do a sum of the series, what do we get? We get 1 into 2 raised to the power n minus 1 divided by 2 minus 1, which is 2 raised to the power n minus 1. That's the number of movements we need to make for a given n. If you put n equal to 3, you will get 2 raised to the power 3 minus 1. If you put n equal to 2, you will get 2 raised to the power 2 minus 1, which is 3.